Welcome to the final lesson of our Linux Fundamentals for Modern IT series. Today we will bring together many of the concepts we have learned and look at the architecture underneath a Linux system. Don't worry, we are not going deep into kernel development. Our goal is to build a clear mental model of how Linux works. At a high level, we can think of Linux as several layers. We interact with applications and the shell. Applications use system libraries and system calls to request services from the Linux kernel. The kernel manages the underlying hardware. We will look at these layers one by one. Linux separates normal applications from the privileged part of the operating system. Applications, shell, and many utilities normally run in user space. The Linux kernel runs in kernel space and has access to system resources that ordinary applications cannot directly access. This separation helps protect the operating system from faulty or malicious applications. The Linux kernel is the core of the operating system. It manages important resources such as CPU, memory, storage, networking, and hardware devices. We have already encountered many of these areas in previous lessons: processes, services, networking, and storage. The kernel is underneath all of them. When we start a program, Linux creates a process to run that program. In our process management lesson, we used commands such as ps, top, and kill to view and manage processes. Behind the scenes, the kernel is responsible for scheduling processes and allocating CPU and other resources. We are not learning these commands here, we are simply using them to see the architecture in action. Processes also need memory to run. Applications normally work with virtual memory, while the kernel manages how that memory maps to physical RAM. This command gives us a view of the memory usage. The kernel is responsible for managing those memory resources. In our previous lesson, we learned about disks, partitions, file systems, and mount points. When an application needs to read or write a file, the request eventually goes through the operating system and kernel before reaching the storage device. We have learned df-h in our storage lesson. The same layered approach applies to networking. An application doesn't normally communicate directly with the physical network hardware. The Linux networking stack and kernel handle that communication. We have already learned networking and SSH earlier in the course. Now we are looking at where those concepts fit within the overall architecture. Let's go back to the thing we have used throughout this entire course, the command line. When we type a command, Bash interprets what we have entered and starts the appropriate program. That program may need services from the operating system, so it makes requests to the kernel. The command itself isn't necessarily a system call, rather, the program executing the command can make one or more system calls to request kernel services. A system call is an interface through which a program requests a service from the kernel. A program might ask the kernel to open a file, create a process, allocate memory, or communicate over a network. So system calls form an important bridge between user space and the kernel. Let's put everything together using a simple example. Suppose I type a command in the terminal. I enter the command, Bash interprets it and starts the appropriate program. The program may request services from the kernel through system calls. The kernel determines what resources are required. Finally, the appropriate system resources are accessed. So, a simple command that looks instantaneous to us can involve several layers working together. We have also learned about Linux services and systemctl. Those processes depend on the kernel for CPU, memory, networking, storage, and other system resources. Now we can see why the subjects in this course are not isolated topics. We use the shell to interact with Linux. Programs run as processes. Background applications run as services. Applications communicate through the networking stack. Files and data ultimately depend on storage. The kernel manages the underlying resources. Everything is connected. Let's make the architecture a more concrete. I will run a simple ls command and then we will look at what happens behind the scenes. Strace allows us to observe the system calls made by a program. You can see that the simple ls command involves many interactions with the operating system. You don't need to learn strace for this course. I am showing it simply to give you a glimpse of what happens underneath an ordinary Linux command. Let's summarize the architecture. User interact with applications and the shell. Programs request operating system services through system calls. The Linux kernel manages CPU, memory storage, networking, and devices. The hardware performs the actual physical work. This is the mental model I would like you to take away from this lesson. Congratulations! And with that, we have reached the end of our Linux Fundamentals for Modern IT series. If you have followed this series from the beginning, you have covered Linux basics, file systems, commands, permissions, users, processes, services, networking, SSH, file transfer, logs, cron, bash scripting, storage, and finally Linux architecture. You have now a foundation on which you can build more advanced IT skills. Linux is an important foundation for modern DevOps. So this isn't really the end of this journey. In the next playlist, I will build on this Linux foundation and start exploring DevOps concepts and tools. If you would like to continue that journey with me, please consider subscribing to the channel. Thank you for joining me throughout this Linux Fundamental series. I hope these lessons have helped you build a stronger understanding of Linux and given you the confidence to explore it further. If you found this series useful, please like the video and subscribe to the channel. I will see you in the next learning journey, DevOps Foundations.